Hi, my name is Alex Kasdin, and I am going to talk to you as I press the buttons to share my screen. Um, we are going to be sharing with you how we incorporate climate change into our species status assessment framework. So I'm going to start just by providing you a brief overview of what species status assessments are. And then Aimee Crittendon is going to share with you how we use the Climate Toolbox, which is a nifty website that the CASC has helped to put together for these species status assessments. And then John Gannott is going to share with you how we're going to streamline this process even further with some new tools that the CASC has helped create. So first, I'm going to be super brief and share with you what species status assessments are in case you are unfamiliar. And I just want to say that I borrowed these graphics and slides from the SSA framework, so I cannot take credit for them.
And Alex, we cannot see your slides if you think you're sharing them.
Oh, I am sharing them. I don't know why you can't see them. I did exactly what we did before.
Okay, maybe now something's happening. Yes, we see that. And if you want to go into slide share mode. Oh.
Can you see them now?
Yes.
Okay, well, there was nothing on the preceding slides. This is the only money slide, so I think we're okay.
Thanks.
So I just want to say that I borrowed these graphics and slides from the SSA framework, so I can't take credit for them, but I will do my best to explain what they share. So species status assessments are the framework that we use to analyze a species' viability to inform decisions under the Endangered Species Act. SSAs might inform whether to list a species or whether to delist a species. They may also help us do 5-year status reviews or draft recovery plans. They are a systematic peer-reviewed way of characterizing the species' resiliency, redundancy, and representation, or what we'll call the 3 Rs, which we also use to characterize viability. So quickly, resiliency is the ability to sustain populations in the face of stochastic events, or for populations to recover from years with low reproduction or reduced survival. It's associated with population size, growth rate, gender ratios, habitat quality, and quantity. Redundancy is the ability for a species to withstand catastrophic events for which adaptation is unlikely. It is associated with the number and distribution of populations. Representation, finally, is the ability of a species to adapt to changes in the environment, and it's associated with the species' ecological, genetic, behavioral, morphological, or any other form of diversity. So viability is the ability of the species to maintain multiple, redundancy, sustaining populations, resiliency, across the species' ecological settings, representation, in order to withstand catastrophes, redundancy, environmental stochasticity, and changes in environmental conditions. So the basic structure of an SSA analysis is that we first identify the habitat or demographic factors that a species needs to be resilient to withstand those stochastic events. This might be that the species requires certain food sources, certain soil types, or a particular number of individuals in a population. A common species need that we consider is whether the species has any particular climatic requirements. For example, do they need a certain amount of water available or temperature tolerance? It is rare that we have studies informing these thresholds, telling us exactly how much water a species needs or that they will wither away above a certain temperature. So the methods that we will show you today make an assumption that the range of the climatic variation that the species has experienced in the historical past represent climatic conditions that the species needs and tolerates. So after identifying these species needs, we then identify whether those needed resources are currently available to the species and whether the species currently has the demographic conditions it requires. This characterizes the species' current conditions. That's this second box here. And then we project forward whether these needs will be more or less available in the future under multiple different scenarios. And that's where climate modeling comes into play. So in this graphic, the green and red habitat and demographic boxes represent species needs, either resource needs or demographic needs. And climate change may be one of the anthropogenic or environmental factors that we consider that can influence the current or future availability of those needs. We might also consider other stressors like grazing or collection that can reduce the availability of these needs, or conservation efforts that can increase their availability. So if we identified a climatic variable as a habitat need or resource need, we would need, let's say, water availability. We would need to analyze whether the species currently has enough water available to meet that need, and how that water availability might change in the future given changing stressors like climate change. In order to do this, we typically need to understand the current average levels of precipitation, temperature, et cetera, and how these values could change in the future under multiple different climate scenarios. I'm going to pass the baton to Aimee now. So Aimee, just let me know when you need me to progress in the slides.
Sure. So I'll start by saying that there are no two SSAs that are the same. Every species is different. The amount of and quality of the data that we have is different. So SSAs can vary drastically depending on the amount of data we have, our understanding of the species stressors, our understanding how the species responds to those stressors, and our ability to project this information into the future. But like Alex said, there are two things that are common to all SSAs, and that's an analysis of the current conditions and an analysis of the plausible future conditions. So today I'm just going to use one example, one SSA from the Colorado hookless cactus as an example of how we used climate data from the climate toolbox to inform the current and future conditions. So next slide. This is a condition category table. It's common in a lot of SSAs. It's basically a set of thresholds for demographic and environmental variables that's used to explain how well the species needs are being met. And we use this to measure the resiliency of each population of the species or each analytical unit of the species. We measure the current status of each of the metrics in this table, and we also predict how each will change in the future. So you can see here, we use summer water deficit as one of our metrics to assess the condition of Colorado hookless cactus. So we know water is an important resource for the species. The species is adapted to a semi-arid climate, but it's still a plant, needs water to survive and reproduce. No one has directly measured the soil moisture in the species habitat. So we use the climate toolbox looking for something that could tell us about historic, current, and future soil moisture conditions for the species. Summer water deficit is a combination of multiple climate variables that represent both the supply and the demand for water. So we use that as a proxy for drought and soil moisture, and ultimately telling us the availability of water for the species. Next slide. So in the climate toolbox, there are a lot of different tools available to visualize and to download historic and future climate variables. So in each of the tools, you can choose which variables and timeframes you're interested in. You can also define the location of the species habitat. So the toolbox will deliver downscaled climate data that's specific to your chosen area. And this was especially important for a narrow endemic species like Colorado hookless cactus to be able to get data that's relevant just to the species climate requirements, not a larger regional assessment that includes habitat that's over 4,000 feet higher in elevation than where our species exists. Next slide. Being able to quickly see this information in a scatter plot or a backsplot or something like that is really helpful for initially getting acquainted with what information is available in the climate toolbox. But once we knew what variables we were moving forward with, we wanted the raw data to develop our thresholds. And in each of the tools, there's a download button that lets you do that. Next slide. So when we downloaded the data, it gave us a file. It contained all of the data we'd selected from the drop-down menus. And we dropped that into Excel workbooks to compare the historic climate data to the demographic data that we had for our species. So like Alex said, we can assume since the species is still here and thriving today, it's able to withstand the climate conditions that it's experienced in the past. But also, those past years gave us an indication of how the species responds to climatic fluctuations. So using monitoring data, to identify historically good and bad years for the species, or years where the species experienced either high germination or high mortality rates. We were able to compare those good and bad years to the historic water deficit levels in those years and come up with the thresholds that we put into our condition category table, and essentially use these thresholds to rate the current and anticipated future conditions. Next slide. So back to our condition category table. For this species, we decided that anything within 1 standard deviation of the historic mean was considered high condition. Within 2 standard deviations of the historic mean was moderate, and anything greater than 2 standard deviations from the historic mean was low. Now, this is a hardy species that doesn't have a strong response to drought. We also used a similar approach for another SSA where that species is much more vulnerable to drought conditions. So in that case, we used a half standard deviation instead of a full standard deviation to delineate those thresholds. And the reason I'm pointing this out is that the data can inform these thresholds, but it's still our responsibility to figure out what are these data telling us about our species. So then our next step was to determine the current condition. And to do this, we calculated the mean summer water deficit for the most recent 10 years and compared that to the historic mean. And then looking at this condition category table, where did that fall within the thresholds that we had defined here of high, moderate, or low? Next slide. So looking into the future, it would be impossible for us to analyze every possible combination of predicted changes in stressors, land management, environmental factors. So what we do instead is we bracket the range of plausible future scenarios. So what's the best case scenario we can reasonably foresee, and what's the worst case scenario that we can reasonably foresee? And then we also generally add a kind of middle of the road scenario that represents a continuation of current trends. So for the climate portion of this, the interactive tools in the climate toolbox were really helpful, especially this future scatter tool. It was helpful in helping us bracket those best and worst case scenarios. So with this tool, we can see 2 variables at a time and see the variation among all of the different model outputs. So here in this example, we're looking at the projected changes in precipitation and mean temperature over 3 different future time frames. So like I said, we want to capture that range of plausible future scenarios. So rather than analyzing how every single one of these modeled projections would impact the species, we use this tool to choose just a few models that represent that range of future projections. So for the hookless cactus, our foreseeable future was mid-century. So we were really only interested in the model results for that time frame, which in this image is the light pink dots. So in the lower right of our time frame, we have the models that predict a larger increase in temperature and a decrease in precipitation. So these are our hot and dry scenarios. And then in the upper left, the temperature is still going to increase compared to the current mean, but not as much as our hot and dry projections. So, and also here, there's a predicted increase in precipitation. So these are warm and wet scenarios. So we can just choose a couple of these models that represent the entire predicted changes in climate. And then we use the future projected values from those models that we choose and compare them to the historic mean that we calculated before, and plug in those differences to our condition category table, just like we did to compare current condition to the historic mean. And that tells us the future condition for the climate metric in each of our future scenarios in our SSA. Next slide. So in our SSA report, here's what that looks like. The table on the left is our optimistic scenario. This measures the resiliency of each of the analytical units or populations of our species. And then on the right, we have our pessimistic scenario. And you can see in our pessimistic scenario, the summer water deficit changes enough to drop that metric into a moderate category. So that means that predicted future scenario is more than one standard deviation different than our historic mean. But in our optimistic scenario, although there's a change in water deficit, it's a slight change and it's still within that one standard deviation of the historic mean. So the condition remains high. And I will hand it over to John now.